Bill and Shell, and I have the great honor of doing the introductions for the last three talks. And so the first talk we're going to have is from Professor Lynne, University of Tennessee, Knoxville. But as of January 2015, so it says this in your bio in the past tense, and I guess it is the past tense now, since we're in January. She is the director of IIS Directorate at the National Science Foundation. Thank you.
Thank you very much. So good afternoon. I'm wearing my University of Tennessee hat at the moment. So I'm going to tell you something about the research that we've been working on recently. It's in the area of what we call peer-to-peer human-robot teams. Many of you have obviously studied human-robot interaction and human-robot teaming. And it means different things to different people, but we all, I think, recognize that robots and humans working together have many applications in society. And so we're all familiar with these various applications. So our work is not any different. We're also interested in all these societal impacts. But the actual meaning, when we talk about peer-to-peer teaming, it means different things to different people. And so if you look in the literature, that term, peer-to-peer human-robot teaming, shows up a lot. But it means different things. It can mean things like humans and robots in the same workspace, sort of working face-to-face. It can mean robots in the same workspace working side by side. It can mean a command and control sort of relationship between the humans and the robots. Or it can mean a flat relationship, no fixed hierarchy. And people talk about teamwork and robots and people working jointly with each other. It means a lot of different things. And so our working definition for our research is that we're talking about robots that are working in the same physical space. The robots and the human are cooperative in the sense that they agree on the task. And so they each want the other to be successful because they're all working together. So they're sort of mutually responsive to each other. They have a commitment to the activity that they're working on as a group, and they're there to support each other if needed. So this assumes, in order to accomplish this, of course, the idea of shared common ground that has been put forth by others in the literature. So this is kind of the gist, and what we really want to achieve in our research is to try to enable this interaction with humans and robots working in the same space to be more natural. So what we're trying to do is to push the idea of how can robots implicitly understand what humans are doing, understand their intent and so forth, and then be responsive to that without the human having to directly command the robot, without the human having to tell the robot what to do. It's not to mean that gestures or natural language are terrible and we never want to use them. But the goal of our research is really to push the envelope in terms of what's possible implicitly. So how can we get humans and robots to work together in such a way that the robot just pitches in as if they were a human on the team in some way that's consistent with the goals of the human. This is really what we want to do. There are several examples of this. Of course, we've seen search and rescue. If you look at these kinds of applications, you see that you have a bunch of people that are working together toward the same objective, but there's not one person necessarily telling the others what to do. These are groups that have practiced together. They know how to do a task collectively, and they don't have to constantly tell each other what to do because they all pitch in, they know what the overall mission is, they know each other, and so they know the skills and capabilities of each other, and therefore they adapt how they do their task as a collective based on that knowledge. So this is what we would like to be able to do, is to throw in humans into a context like this and have the robots, throwing robots in a context like this, and have the robots just pitch in an appropriate way. Another example is like a fire team of soldiers that may be clearing a building. They're going through the building to try to find dangers of some sort. You would want the robot, if it's helping, perhaps a some point robot to help clear the building, to be able, again, to pitch in and know how the team works. This only works through practice in the sense that the whole team knows how to work together as a whole. You don't throw a bunch of people together that have never worked together and expect it to work smoothly without any explicit cooperation. You do need the practice. So we're presuming that these teams have worked together, they know each other, they know how to do the task, and now here you are in the moment, in the application, and you want to work together as smoothly as possible. So this is our objective in the research, is to see what are the technologies and the algorithms that need to be developed in order to allow a robot to implicitly collaborate with human collaborators without having to be told what to do. Obviously, it's a very hard challenge. And so there are a lot of technical issues that have to be addressed. Foremost, the robot has to understand what the goals and intentions and actions are of the human teammates. You can't expect the robot to pitch in a proper way if it's not properly understanding what the objective is of the human team. Now, you can drill down at multiple levels, and Regina talked about this some yesterday in terms of understanding the intent of humans. You can look at it at a very high level, or you can look at it at a low level, like a task. And so these are multiple levels of challenges from a research perspective. There's a question of how do you represent human and robot capabilities. And then let's say the robot perfectly understands what the human's intent is and what the human's activities are, then, which is a hard challenge, a big presumption. But if you could presume that, then the question is, how does the robot know what to do in order to pitch in a helpful way? So this is kind of an action selection problem in this context. And then, of course, you have all the real-world challenges of things changing dynamically, so you have to adapt, you have to make sure that you have reliable systems and robust systems. So this outlines a very long research agenda that you could work on for the entire career. And so what we're trying to do is to see what are the most fundamental missing gaps that we can develop to let us get towards this peer-to-peer human-robot teaming in practical applications. So this is, in our research, we have a long history of looking at interactions with team members, particularly robot team members. But the missing piece for having a robot to join in with humans in our work is the whole perception challenge. So we focused in the last 2 or 3 years on the whole perception challenge. And so what does that mean? So with the advent of the Connect, and we all have Connects, that helps us to gather important information from our environment, the environment that's global to the robot, so that we can use that, the robot can use that, to begin to understand the actions and activities of the human. Now, there's been a lot of work in human activity recognition. In our domain, we're talking about robots that are physically side by side with humans, not in observing them from afar. You have real-time issues. You have the real-time issues of the human and the robot, where the robot has to actively make decisions right then and there to pitch in terms of what the human is doing. You have motion issues because the robot is moving as the human is moving in a dynamic environment that affects your field of view and so forth. So there are a lot of challenges here. But from the visual data, we can look at some object recognition issues, the human tracking and detecting issues, how you represent the human, how you understand the human activity, and then finally, you want the robot to pitch in. We call this last piece risk-aware action selection because we know that all of these techniques up to this point of the robot trying to perceive the current state of the human team members is a noisy process. We know it's probabilistic. The robot may be wrong. The most classification algorithms these days, they're good if they're in the 90 percentiles, but they're not 100, and it's not easy to have 100% correctness. So we know that the robot might be wrong in understanding the current activity of the human team members. So you want the robot to pitch in a way that takes into account the question of what happens if it's wrong. And so that's why we call it risk-aware action selection. We want the robot to be aware of the risk of being wrong when it selects what to do, so that maybe it can perhaps change its actions to be familiar with that. So this last piece is what we're working on more recently. And so I'm not going to report on that at this moment, but I'll just tell you in a broad brush survey of some of the work that we've been doing in these other areas to contribute to the robot's ability to understand the current activities of a human in the same workspace so that then they can work together in a human-robot peer-to-peer team. So this is our overall research agenda.
Ready. Simon says, rub your belly.
Okay. Let me stop with this to explain this for just one moment. So when you have humans and robots working together in the same workspace, you obviously need a robot that's capable of doing some human-scale task. We've historically used a lot of Pioneers and little Now robots, but, they can have a tea party with you, but maybe doing a human-scale task is not quite so practical. So we recently got this robot. It's from Meta, which was one of the acquisitions of Google not so long ago. But this Meta robot has two 7-degree of freedom compliant arms, series elastic actuators, has two hands that can grasp objects. It has a fairly rich sensor head here with an ACES depth sensor and various types of cameras, stereo cameras and high resolution cameras. And its whole torso here is on a Z-lift, so it can go up and down to achieve different heights. And then its base is an omnidirectional base, and so it can move around the environment. So this gives us a robot that's able to do tasks around an office building and an academic building that are sort of at the level of a human. If you notice that picture of me with the robot on the first slide, it's approximately human size. So this gives us the ability to do practical tasks. So this is just a little fun video that just shows some of the motion capabilities of this robot. We've integrated into it a speech recognition system, and it's just playing Simon Says. And so the speech recognition part is not really part of our implicit cooperation, but just to give you a feel for this robot.
Ready. Simon says, raise your arms. Okay. Ready. Flap your arms. You didn't say Simon says. Simon says, flap your arms. Okay. Ready. Look down. You didn't say Simon says. Simon says, look down. Okay. Ready.
Okay, so that's just a fun video, just showing you the robot and the scale of the sorts of things that you can imagine a shared task might be. So, in this context, our experiments that we've been developing for the robot to understand and perceive the capabilities of a human are based on all the sensors that are mounted on the head of this robot. So the research data that you'll see going forward in my final few minutes are coming from this sensor suite here on this robot. So, the questions then in terms of how do you have the robot understand the current context of the human fundamentally begin in the whole perception challenge. And so we've made some contributions in various areas. I don't have time to talk about all of these. I just want to give you a broad brush. But we've looked at some new features that help us with interpreting depth in the context of humans. When we first started this work, the Connect had just come out about 3 or 4 years ago. And so we defined some new features that use depth that we found to be very handy for this peer-to-peer teaming with the robot in the workspace of the human. And we've also identified some other new features that have some nice properties specifically for human activity recognition, but they're broader. We know that we often have robots working with teams that have multiple people and multiple robots. And so there's some interesting challenges of how to make sure that you're making distinct understandings of the different people in the environment and not mixing them together. Then, of course, there's a problem of understanding human activities, and I mentioned the risk-aware action selection. So we have a lot of papers that talk about the technical details here. I'm not going to go into many of those details, but there are details available. So first, let me just talk about a couple of the features. The depth of interest feature is a feature that allows us to make use of the depth information in the connect in order to better localize humans in the environment. So it's a feature that can operate in real time. It also accommodates the camera movement because the robot is moving. And it allows us to deal with some of the real world perception problems in this domain. In order to demonstrate the effectiveness of this depth of interest feature, we did apply it to a human activity recognition problem. And so that technique, I'll tell you very quickly about here, and then we'll just give you an idea. So I don't have a lot of time. The gist of this feature is to, rather than having representations that are like a human, like a 3D centroid or shape history or a motion sequence of human models, we use a local spatial temporal features. And so there are lots of possible features that have been developed in the past that are these local spatial temporal features. Ours adds the depth. And so the idea, if you're not familiar with the local spatial temporal features, is that you can locally understand what's happening in your image during a human activity, and then each of these local features then give you, you're familiar with bag of words technique, so it gives you a bag of possible features, and then the distribution of those features gives you an idea of what activity is most likely in the distribution of these local features. So the 4D depth of interest feature detection allows us to take into account the depth. And so it builds upon some of these prior feature techniques, but it adds in the depth. And I don't have time to go into the details, but you apply filters along both the spatial and temporal dimension. And then you're able to pull out a combination of the intensity and the depth image into one feature that then you can apply across the image, and then you extract from these the features that are relevant for your application. So the features then can come together to allow you to create code words. Many of you may be familiar with the LDA techniques, and so this leverages those techniques in order to build up a model. This part is just for human activity recognition, but it uses this new feature that I mentioned. And so this then allows you to look at the mapping of these local spatial temporal features to activities, and then look at a whole stream of these activities as the robot is watching the human in the environment to determine which activities are happening at each point in time. This just gives you another feel for what the idea is about. A code book is just all these local features. A collection of these gives you a distribution across a particular activity, and so then from that you can map from the local features from the distribution of that to the actual activity. So this is the general technique for doing the activity recognition, but using the new feature that we developed. And so we've evaluated this in a lot of contexts. At the time we did this work a few years ago, there were no data sets that included depth. So we created a new data set that includes depth and human activities, and then demonstrated the ability of this to work well for human activity recognition. This just shows you a very quick video of this depth of interest detector and in different activities and how it shows up in these sorts of activities. The nice thing about this depth of image feature is that even though you can use a learning technique that does not model sequential activities, it does not directly model time, the feature itself allows you to extract some time measurements because we actually connect in time these cuboids that have these depth features. And so what turns out is that when you look at some activities that can only be distinguished if you look at a series of the activities over time, like sitting and standing. If you take a snapshot of a sitting in the act, you can't tell the difference between in the process of sitting or in the process of standing. In one moment in time, they look identical. You can only distinguish them if you look at the sequence of activities over time. This feature allows us, nevertheless, to distinguish between these two. The lifting and the removing are exactly identical, but reverse activities. And you can see we can get a very high distinction between these two because the feature itself incorporates some time dimension into it. I don't have a lot of deep time, so let me just move on to say that's one of the things that we did was to define this new feature that works well in the local domain of humans and robots working in the same workspace. And you can apply this to multi-human detecting and tracking, and so we've done that, and it works quite well. And you do this in real time. So when you have robots that are working with multiple humans, then this applies very well. We developed another feature that takes into account some of the limitations of prior descriptors for 3D systems, X, Y, time, that are commonly used in human activity recognition. So we call this a Simplex-based orientation descriptor. This is a descriptor that we've shown overcomes some limitations with existing 3D descriptors that are commonly used in activity recognition. And so the gist of this is to overcome two main challenges. One is that if you have a spherical coordinate descriptor, you see that the bends near the equator of this are much larger than the bends at the poles. This causes you to have a much reduced granularity. And then they're often, polyhedral-based descriptors are often used, but these have limited descriptive power because you have a limited number of polyhedrons with which to describe your features. So we developed a new technique that's called, based on the Simplex, which scales to any dimension so that you don't lose the fidelity of the information that's in your image. It maps your 3D features more directly to the Simplex space so that you have much better outcome. And so we compared this to several existing descriptors for human activity recognition and showed that the feature matters. And so our technique, here you see on the bottom, gets a better performance compared to a lot of existing detectors. This is true for several different data sets. The only techniques that have been published in the literature that are better are techniques that combine multiple descriptors. Ours is a single descriptor that you can then combine with other descriptors. So according to all these other techniques that we compared to, ours does really quite well. So the point is, how do you represent the features in your human activity recognition has an impact on the fidelity of your approach. So that's a lot of the work that we've been doing. We've been looking at work on sequential human activities, which means that people don't just do one activity and then stop, but they do one activity, then they go to another activity and another activity. And Regina yesterday mentioned the segmentation problem. You don't know when you're going from one activity to another. So we've developed a technique in Regina's work. She talked about repetitive tasks. We're looking at tasks that go from one activity to another, not repetitive, but how do you tell when you're going from one to another? And these also happen in a continuous manner. So we developed techniques for these as well. I'm out of time, so I'll just go here to the end and say this is kind of a broad program that we're working on of trying to get robots to work together well with humans as peers. And so we've been focusing in the recent years on the perception problem. What we're now focusing more on is how, once you perceive what the human activity is, how does the robot pitch in a way that's appropriate according to this risk-aware technique that I mentioned earlier. So with that, I'll conclude. I want to acknowledge the students that have been working on this project. And if there's time for any questions, I'm happy to take.
I think we have time.
Great talk, and thanks. In almost a past life at this point, Manuela and I dabbled in the idea of peer-to-peer human-robot teams in sort of gut sense. One of the things that always struck me was if you're truly peers, then it's got to go both ways, right? So you talked a lot about the robot recognizing the human activities. One of the other hard things is sort of exposing the state of the robots to the humans, right? I was just curious your thoughts.
Yeah, that's exactly right. And we acknowledge that that's a really important part of the problem, and that's not something that we've looked at yet. But clearly, it is two-way. And so that, I don't deny that's very important. Yeah, but that's not the space that we worked in. So
Fair enough. Thanks.
Okay, that's one
Okay,
more.
thank you.